Hi, welcome back again to our next section on calorimetry. In this section, you're going to be able to describe how to measure and calculate the quantity of energy transferred as heat in a reaction by calorimetry. So the energy evolved or absorbed as heat in a chemical or physical process can be measured by calorimetry. The apparatus used in this kind of experiment is called a calorimeter. So we're measuring the heat flow with the calorimeter. It can be thought of as a closed system. So a constant pressure calorimeter can be used to measure the amount of energy transferred as heat under constant pressure conditions. The enthalpy change for a chemical reaction can be measured. So when we're measuring that enthalpy change, we're measuring Q for the reaction. RXN stands for reaction. Remember that the reaction plus the solution heat, equal and opposite, will equal 0. Here's an example of what we're going to call our coffee cup calorimeter. This is an inexpensive device that consists of 2 nested styrofoam coffee cups with a loose fitting lid and a thermometer. All right, so we can see one cup within another, and we have a loose lid and the thermometer's poking through it. Styrofoam is a fairly good insulator, and it minimizes energy transfer as heat between the system and the surroundings. The reaction is carried out in solution in the cup. If the reaction is exothermic, it releases energy as heat to the solution, and the temperature of the solution rises, and we can measure that with a thermometer. A decrease in temperature of the solution will be seen if the reaction is endothermic, so energy is absorbed as heat from the solution. And again, we would see that as a temperature drop. The change in temperature of the solution is measured. Knowing the mass and the specific heat capacity of the solution and the temperature change, the enthalpy change for the reaction can be calculated. Now, in this type of calorimetry experiment, it's convenient to define the chemicals and the solution as the system. So this is our system. The surroundings is everything outside of our coffee cup calorimeter. So the surroundings are the cup, everything beyond the cup. But as we just said, we assume there is no energy transfer to the cup or beyond, and that energy is transferred only as heat within the system. So there's 2 energy changes occurring within the system. One is the change that takes place as the chemical reaction occurs, either releasing the potential energy stored in the reactants or absorbing energy and converting it to potential energy stored in the products. So we're going to label that energy as Q. The other energy change is the energy gained or lost as heat by the solution. So based on the law of conservation of energy, flipping back here, based on the law of conservation of energy, we can say that the value of Q solution can be calculated from the specific heat capacity, C, also the mass, and the change in temperature of the solution. The quantity of energy evolved or absorbed as heat for the reaction, so Q reaction, is the unknown in the equation, and we know that this plus that is equal to 0. Let's look at an example here. Let's say that we place 0.5 grams of magnesium chips in a coffee cup calorimeter and then add 100 milliliters of 1 molar hydrochloric acid. So we have magnesium plus hydrochloric acid, and we have a single replacement reaction here. So we're able to write our reaction as magnesium solid plus 2 HCl. Magnesium is going to kick out the H, so we have H2 plus MgCl2. Now it also tells us the temperature of the solution increases from 22 degrees Celsius to 24.46 degrees Celsius. So we can find our delta T here. What is the enthalpy change for this reaction per mole of magnesium? We also are going to assume the specific heat capacity for the solution is, and we're given our C, and the density of HCl is 1 gram per milliliter. Assume no energy is transferred. So what do we know? We know that we're given a mass of 0.500 grams. So we need to find the amount of magnesium, number 1, because whenever we have grams, we need to get to moles. Right. All right. So that's step number 1. Step number 2, we need to calculate Q of the solution, the heat of the solution, from the values of the M, the C, and the delta T. Number 3, we need to calculate Q for the reaction, assuming no energy is transferred as heat. So we know that Q of the reaction plus Q of the solution is equal to 0. And then step 4, we're going to use the value of QR and the amount of magnesium to calculate the enthalpy change per mole. So let's get started on that. Let's look at the next page. So we said step number 1. I started with grams of magnesium. I'm going to go to moles of magnesium. So if I look at the periodic table, I see there's 24.31 grams of magnesium. So that gives me 0.002057 moles of magnesium. Let's find the Q of the solution. The mass of the solution says that they put in 100 milliliters, and they said assume the density is 1. Remember, density is mass divided by volume. So if I know density is 1, and I know volume is 100, to find mass, we just cover up mass, and it's 1 times 100. So it'd be 100 grams of HCl. So I have 100 grams of HCl plus 0.05 grams of magnesium. That's my whole solution. We got to add them both together. Then I'm given the specific heat of the solution, and I know the change in temperature for the solution. So M times C times delta T. And I get 945.5 joules. I'm not going to round significant figures until the very end. Okay, so now let's find QR. So we know that QR plus Q solution is equal to 0. If Q solution is 945.5, QR is going to be negative 945.5. So now let's find our delta H per mole of magnesium. Okay, so I just need to take my QR, right, joules per mole. So I need to divide it by what I found. How many moles of magnesium was that? So negative 945.5 divided by the moles of magnesium to get how many joules per mole. Let's look at another example. Assume that 200 milliliters of 0.4 molar HCl is mixed with 200 milliliters of 0.4 molar NaOH in a coffee calorimeter. The temperature of the solutions before mixing was 25.1. So we have a initial temperature. After mixing, allow the reaction to occur. We have our final temperature, TF. What's the enthalpy change when 1 mole of acid is neutralized? We have HCl plus NaOH, and it's going to neutralize, right? We know that an acid plus a base is going to make water and a salt, in this case NaCl. First step, we're given, let's find the mass of our final solution. I know that I added 200 milliliters, or 200 grams, and 200 milliliters, also 200 grams. Again, it says assume the densities are 1, same as water. So 200 milliliters is 200 grams. So 200 and 200 is 400 for our final solution, because we need to find the Q of the solution, which means both mixed together. All right, we know our change in temperature. We just wrote TF minus TI, so we have our change in temperature. We're going to use the Celsius. We don't need to use the Kelvin. To find our amount of hydrochloric acid used, which is equal to our amount of NaOH used, we're going to do C times V, so our 0.4 moles per liter, which is molarity, times 200 milliliters is 0.2 liters, right? So 0.4 times 0.2 gives us 0.08 moles of HCl. So now we just need to do some math here. So let's find Q of the solution. Our M, our 400 grams, right? Because our Q of the solution, SLN, I'm just going to abbreviate, solution is SLN, is M times C times delta T of the whole solution. The whole solution has 200 grams plus 200 grams, so 400 grams times the specific heat of the solution, 4.20 joules per gram Kelvin, which is the same as degrees Celsius, time M times C times delta T. The change in temperature was 2.68. When we multiply that together and get our Q of the solution, we know that a Q of the solution would equal 4.502 times 10 to the third joules. So the Q of the reaction is the opposite, remember, because Q of the reaction plus Q of the solution is equal to 0. Okay, so that's for the whole reaction. We want to know per mole, what's it say? 1 mole of acid. All right, we know how many moles of acid we have. 0.08 moles of acid. We did that. Remember, we took the molarity of the acid, 0.4 capital M, way up here at the beginning. 0.4 capital M means moles per liter. And we know that we had 200 milliliters of it, which is 0.2 liters. This is all for HCl. So we figured out how many moles of acid there was. So now, to find out energy per mole, I'm going to take my energy, negative 4502 kilojoules, divided by 0.08 moles, and I should get negative 56.3 kilojoules per mole for HCl. So constant volume calorimetry, measuring delta U, or internal energy, is often used to evaluate the energy released by the combustion of fuels and the caloric value of foods. So a weighted sample of a combustible solid or liquid is placed inside a quote-unquote bomb. Often it's a cylinder about the size of a large fruit juice can with thick steel walls and ends. And here's a picture of it. The bomb is placed in a water-filled container with well-insulated walls. After filling the bomb with pure oxygen, the sample is ignited, usually by some kind of a spark, and the heat generated by the combustion reaction warms the system. So the bomb, its contents, and the water are defined as the system. And then we assess the energy transfers as heat within the system. Q of the reaction plus Q of the bomb plus Q of the water all equals 0. Again, because law of conservation of energy cannot be created or destroyed. So QR is the energy released as heat by the reaction. Q of the bomb is the energy involved in heating the calorimeter bomb. And Q of the water is the energy involved in heating the water in the calorimeter. Now, because the volume doesn't change in a constant volume calorimeter, energy transferred as work does not occur. So the energy transferred as heat at constant volume is equal to the change in internal energy. So we have octane, which is a primary constituent of gasoline. It burns in air. So we have octane plus oxygen to give us CO2 and H2O. So we're told that we have a 1 gram sample of octane, and it's burned in a constant volume calorimeter, similar to shown the one that we just looked at. The calorimeter is in an insulated container with 1.20 kilograms of water. The temperature of the water, again, so we're given water, the temperature of the water rises from 25 to 33.2 degrees Celsius. That's information we need to know. The heat required to raise the bomb's temperature, its heat capacity, so the C of the bomb, is 837 joules per Kelvin. What is the heat of combustion per gram of octane? Okay, so the first thing we need to look at is we need to remember that QR plus Q of the water plus Q of the bomb is all equal to 0. So let's find the Q of the water first. So we know the Q of the water is M times C times delta T of the water. Okay, so what's the mass of the water? 1.20 kilograms. I want this in grams. So let's change this. 1.20 kilograms is 1,200 grams. So we're going to use 1,200 grams times the specific heat of water, 4.184 joules per gram degree Celsius. And let's look at our change in temperature of the water, which is 33.2 minus 25. So 8.2 degrees Celsius. So our Q of the water, we should get 41,170.56 joules. All right, so that's 1. Next, let's find the Q of the bomb. Heat capacity is 837 joules per Kelvin. And if you think about how to find heat in joules, if I'm given joules per Kelvin and I just want joules, I have to multiply by my delta T, my change in temperature, right? So 8.2, we know 8.2, the change in temperature, 8.2 degrees Celsius is equal to 8.2 Kelvin. So that will cancel out my kelvins and will give me just joules. So 6836.4. Okay, so let's find the heat of combustion for my octane. Now remember, QR, so for my reaction, plus Q of the water, 41170.56, plus the Q of the bomb, 6836.4, equals 0. So if we combine these and then subtract that from both sides, then I would need to subtract that from both sides. So QR is equal to 48033.96 joules. And it wants heat of combustion per gram of octane. So here's my heat of combustion for my reaction, and I want per gram. Well, we knew that we have 1 gram of sample of octane. So I'm going to divide it by 1.00 gram of octane. So obviously this divided by 1 is going to give us the same thing, and I want 3 significant figures. So 480, and then these we'll put just as placeholders. So 48,000 joules, or we can say joules per gram, joules or 48 kilojoules for part A. Part B says, what is the heat of combustion per mole of octane? Well, we would need to figure out the molar mass of octane. So we would take, we know how many kilojoules, so we would take my 48 kilojoules per gram, right? This is kilojoules per gram, as I did joules divided by grams, and we changed it to kilojoules per gram. And so I need to figure out my molar mass of octane for 1 mole of octane. All right, so if I add up 8 carbons and 18 hydrogens, I should get a molar mass of 114.2. Let's take our 48,000 joules times 114.2. And I get, this is in joules. And again, all I did was take this kilojoules or joules per gram, because I did joules per gram. And I wanted it per mole, so I had my grams and grams cancel out. Figured out the molar mass of octane for 1 mole. Now, what did I do something wrong? Something doesn't seem right. Oh, here we go. I have an exothermic reaction, and when I added these two together, I got a positive number. I forgot to subtract it from both sides. So this should be a negative, which makes this a negative, which makes this a negative, and this is a negative. I added these two together to get a positive 48,000, but I had to subtract it from both sides. So 0 minus 48,000 would give me a negative 48,000 to equal my QR. So make sure that you have the correct sign. All right, let's look at our last example for this section. We have a 1 gram sample of ordinary table sugar, sucrose. It's burned in a bomb calorimeter. What is the heat evolved per gram of sucrose? So we are looking at the energy evolved as heat in the reaction. So we need to find this out. We know that energy evolved as heat in the reaction plus energy as heat absorbed by water plus energy as heat absorbed by the bomb. All of those added together is equal to 0. Again, law of conservation of energy. So let's write this out. This we don't know. So we're going to say Q of our reaction plus. Let's find our energy as heat absorbed by water. And we can look at this and go, okay, the temperature of the water, we have this many grams of water, so that's our M. So let's write down our 1,500 grams of water. M, specific heat of water, 4.184 joules per gram degree Celsius. M times C times delta T of water is, it went from 25 to 27.32. So I'm going to write up here, 27.32 degrees Celsius minus 25. Well, that'll just be 2.32, right? Degrees Celsius, 2.32 degrees Celsius. So this is for my water. Energy evolved as heat in the reaction plus water plus energy as heat absorbed by the bomb. Let's see what we can find with that. Well, we know the heat capacity of the bomb is 837 joules per Kelvin. So 837 joules per Kelvin. Remember, I just want joules. I've got joules per Kelvin. So let's times it by delta T. So this is my heat capacity. So C times delta T gives me Q. All right, so what is my change in temperature? We already said it was 2.32 degrees Celsius or Kelvin. Okay, it's equal to 0. All right, let's do our simplifying, and let's do it correctly this time. So I've got 1,500 times 4.184 times 2.32, 14,000. So Q of reaction plus 14,560.32 plus 1941.84. Now I'm going to combine these two together. What do we get here? All right, so I've got Q of the reaction plus 16,502.16 is equal to 0. So I'm going to subtract. So Q of the reaction is equal to negative 16,502.16 joules. I'm going to do a quick how many sig figs. Everything has 3 sig figs. So actually I need to go negative 16500 joules. That's 3 sig figs. The next one, it wants heat evolved per mole of sucrose. Oh, this first one actually, it says per gram. So this gives us joules. Now we would need to divide it by how many grams of sucrose I started with. Well, here I only started with 1 gram. If I would have started with 5, I would need to divide this by 5. Here I'm starting with 1 gram. So I'm going to get the same answer because I'm dividing it by 1. So negative 16500 joules per gram of sucrose. It wants heat evolved per mole of sucrose. So I'm going to take my negative 16500 joules per gram. I got to figure out the molar mass of sucrose. Grams of sucrose per 1 mole. And my molar mass should be 342.3. So I'm going to do negative 16,500 times 342.3. And I should get negative, again, I want 3 sig figs, negative 565, and then 4 zeros, joules per mole of sucrose. Again, this is in joules. If you want to put it in kilojoules, it's just going to be 3 less zeros. So this could be negative 5650 kilojoules per mole, and this would be negative 16.5 kilojoules per gram. Either one works.
If you're following along with the PowerPoint, there are a few extra practice problems, the do at your desk or join-in questions, and I would like to welcome you to try to do these and set them up. So to pause your video and write up everything that you know and try to work through it. And you'll notice that I'll click through and I will post the answers. So in this case, there I would post an answer. So before having that, why don't you pause the video, write down what you know, and figure out what is the question asking us to find. This is very similar to a test setup question. And then take some time to pause the video and work through each step. Here's another question. How did you do? And another one with the work.
In the next video, we're going to move on to enthalpy calculations.